Hi guys. So we just studied proportional controllers. We saw how they can allow us to get an output from a closed loop system that is as close as possible to a certain reference input. However, we also saw that proportional control can sometimes lead to steady state errors. The question is, how do we get rid of that steady state error? Well, we add an integral term to the proportional controller. It then becomes a PI controller or proportional plus integral controller. Let's now have a look at what is a PI controller through a block diagram. So first we start as usual with our reference signal RT. To RT we subtract YT, which is the output of the system, and this gives us the error ET. Now you will recognize KP. KP is the proportional control side of the controller, a controller that is now made of two parallel branches. So here it is very simple. It is as usual, KP is multiplied by the error. However, we also have another branch which is made of a gain Ki followed by an integrator. In this case, Ki is the integral gain. It's a value we have to set ourselves like for Kp. But here, the error is multiplied to Ki and it is then integrated. Now, the amazing thing with Laplace transforms is that integrations and differentiations are super easy. Essentially, an integration is just dividing something by s, while a differentiation consists in multiplying something by s, and we will see this more in detail when we look at derivative control. What's really interesting as well is to think about the fact that s, the way you apply s to an equation actually shows you if you are looking in the past or the future or what you're doing to the equation. So when you integrate something, let's say here we integrate Ki times Et, we actually divide by s. And what it means is that we accumulate all the previous errors of Et to see what happened in the past. If you don't do anything with s, you're actually looking in the present, like a proportional controller does. If you want to look at the future trend of the possible values of the error, you actually differentiate it, and to do that, you multiply by s. So it's exactly what a differentiation does. It just looks at the trends, the future trends, the rates of change of a certain equation, a function, and it allows to estimate potential or most likely future values. So we then do the sum of this proportional control and integral control, and this is a PI controller, which has a part of proportional control, then a part of integral control, and they are then added together. So the controller transfer function is actually GCS is equal to Kp, the proportional gain, plus Ki, the integral gain, divided by S. This gives us the control signal ut is equal to the integral of Ki multiplied by the error, we close the integral, plus Kp multiplied by the error. We feed that into the plant of the system, and this outputs us Yt, and we feed that back again in the error, and so on and so on. So here all we did is we added an integrator. The integrator integrates the error over time and adds to the proportional controller's output. So essentially, all this does is divide the error multiplied by the gain by s. Let us return to our previous example where we had that the plant transfer function GPS is equal to 93.6 divided by s plus 1.95. We need to determine the proportional gain Kp and the integral gain Ki in order to obtain a settling time of Ts equals 0.2 seconds. We will also find out the steady state performance of the system. As in the previous lecture, we start by calculating the open loop transfer function. As you will remember, The open loop transfer function is actually the transfer function of the controller multiplied by the transfer function of the plant. Here, in this case of a PI controller, it is Kp plus Ki over S multiplied by GPS. And we plug in the numbers that we have, we get that Kps plus Ki multiplied by 93.6 is divided by S over multiplied by S plus 1.95. Again, we also have the transfer function that relates the error ES to the reference input RS, and this transfer function is 1 over 1 plus GS. Remember, this is also very important, and it is called the closed loop transfer function. In this case, we can plug in all the numbers, and we eventually get that the closed loop transfer function ES over RS is equal to S squared plus 1.95S divided by S squared plus 1.95 plus 93.6 Kp multiplied by S plus 93.6 Ki. You should remember that the characteristic equation of a system is what gives us a lot of information about its behavior, and it can be found by equating the denominator of the closed loop transfer function to 0. So in this case, that gives us S squared plus 1.95 plus 93.6 Kp multiplied by S plus 93.6 Ki equals 0. So before we move any further, I want to give you a few definitions about the damping of systems. What we call an underdamped system is a system that oscillates until it reaches its final value. An overdamped system is a system that reaches its equilibrium or final value without any oscillations. Finally, a critically damped system reaches its final value as quickly as possible without oscillating. It is basically the type of damping that is at the limit between an underdamped system and an overdamped system. Obviously, a critically damped system is what we are going to try to aim for most of the time. A second order characteristic equation can actually always be written in the form of S squared plus 2S multiplied by a damping coefficient multiplied by omega n plus omega n squared equals 0. So omega n is actually the natural frequency of the system. It is the inverse of the time constant, so 1 over the time constant. And you don't actually have to physically understand it to be able to use it, but it is essentially the natural frequency of the oscillations of the system. So in the case of a critically damped system, which as I said before is most of the time what we want, we actually have that the damping coefficient is equal to 1. Therefore, it disappears from the equation. We also know that Ts, so the settling time, is equal to 4 over omega n. Again, this is a definition of the theory. You can find it anywhere, anytime you want to use it. You can even learn it by heart. It's quite easy to remember. So here, because we want a settling time of 0.2 seconds, we can write that omega n is equal to 20 radians per second. So the characteristic equation in this case becomes S squared plus 40S plus 400 equals 0. So this is the characteristic equation for our system to be critically damped and have a settling time of 0.2 seconds. So now we can equate the characteristic equation we developed for our system with our gains to the characteristic equation we developed to have our system achieve the performance we want. We equate the two and we can develop these two equations. Eventually, we get that Ki equals 4.27 and Kp equals 0.407. It's actually interesting to observe that Kp is roughly equal to Ki divided by 10. It is funny because it is often the case. Therefore, we can write our open loop transfer function to be equal to 0.407s plus 4.27 multiplied by 93.6 divided by s multiplied by s plus 1.95. So the closed loop transfer function for the input-output behavior of the system from RT to YT can then be written Ys over Rs is equal to 0.407s plus 4.27 multiplied by 93.6 divided by s squared plus 40s plus 400. The transfer function for the complete system is now Ys over Rs equals 38.05s plus 400 divided by s squared plus 40s plus 400. So the system now contains a zero, which can cause an overshoot. That zero is due obviously to the s present in the numerator. And this is exactly what we observe when we plot the response of the system. There is an overshoot. The response, the amplitude of the response is actually higher than our reference input C. However, thanks to the integrator, we now have a steady state error of 0. That means that we got rid of the error that was due to the proportional controller, but we also now have a slight overshoot. So in the end, if you're just aiming at reaching a final value in a relatively short amount of time, then the PI controller is perfect. However, if you want to always ensure there are no overshoots, then we're going to have to do other things to make this work. There is one little problem with the integrator that can actually be very annoying. I've actually faced that in many design projects, and when it happens, it takes you by surprise and completely destroys your system and its behavior. So if the error actually never reaches 0, then the integrator will keep increasing and increasing with time towards infinity. And this can lead to great performance issues. For example, this can occur if the control signal is limited and can never reach a value to bring the error to 0. This is called saturation. So imagine you have your integrator which is integrating and increasing, telling your control signal to reach a certain value. However, you put something in your software that says, okay, after all this calculation, now bring back the control signal to that value because it cannot actually be that high or that low. So then the control signal actually never reaches the value that is necessary for it to reach the final output the integrator is trying to make it reach. Hence, the integrator actually keeps increasing and increasing to compensate for this because it integrates the error over time. It accumulates the error that is currently present. So this windup can obviously cause huge damage in your performance, but it can be avoided by actually saturating the integrator itself. So you essentially say, okay, the maximum value the integrator will ever reach will be, let's say, the value D. And attributing that maximum value will make sure the integrator never winds up above it uncontrollably. The advantages of PI control actually are that it gets rid of the steady state error after step input by introducing an integrator 1 over S. However, its disadvantages are that it is more complicated than a pure proportional control. There are now two gains to be determined, and the order of the transfer function is increased by 1. It also introduces a 0 in the transfer function from input to output, and we just saw that this leads or can lead to overshoots. For more complicated plants, the design of an integrator can actually be quite awkward and complicated. And finally, integrator windup can occur, but we have just seen that this can actually quite easily be fixed and avoided. So this concludes our lecture on PI control. If you have any questions, as usual, please do not hesitate to message me. It'll be my pleasure to help you. Thank you very much, guys.